climatic influence on river incision and relief generation. We will build an intuitive picture of how rain, snow, and ice control how quickly rivers carve mountains, and how that shapes relief, the difference between peaks and valleys. First, fluvial incision, cutting by rivers in bedrock, is often modeled with the stream power law. Incision rate equals K times drainage area to the M times slope to the N. Climate enters through discharge, so we can write incision equals K prime times the product of area and precipitation to the M times slope to the N. The takeaway is simple. More water usually means more cutting power. Let's compare two otherwise identical mountain catchments. On the left, a wet, monsoonal climate, big discharge and frequent floods. On the right, a dry, semi-arid climate, low discharge and episodic floods. More water boosts incision, while dryness forces channels to cut slowly. Topography adjusts to climate. For a given incision rate, wetter regions typically have lower required river slopes, whereas drier regions require steeper slopes. That gives a negative correlation between river steepness and precipitation. Climate also sets the rhythm of extreme floods that do outsized geomorphic work. In monsoonal or typhoon climates, big floods happen often and cut bedrock during short windows. In arid regions, rare flash floods may be the only times incision occurs. In cold climates, glaciers can limit mountain heights, the glacial buzzsaw. When peaks rise into the snowline, glaciers form and erode headwalls aggressively, keeping summits from growing far above the equilibrium line altitude. This caps elevations, even if rock uplift is strong. Even without big glaciers, cold periglacial processes can chew down summits. Freeze-thaw weathering creates a weak cap that limits peak growth and feeds debris to rivers. When climate shifts, rivers adjust their long profiles. A jump to wetter conditions increases incision power, often creating nick points that migrate upstream. These leave terraces and inner gorges as markers of transient incision. Relief grows where uplift outpaces erosion, but climate modulates erosion efficiency. Across many mountain belts, relief can be largest at intermediate precipitation and lower in hyper-wet zones, where peaks are shaved by ice and landslides, and in very dry zones, where valleys fail to incise deeply. Case studies reinforce the picture. In New Zealand's southern Alps, very high rainfall and fast uplift produce huge relief in a dynamic, steady state. In contrast, the Appalachians have modest rainfall and little uplift, so relief stays low and slowly decays. To summarize, climate controls discharge and ice formation, which set river and glacier incision. Wet climates tend to enhance incision and lower required slopes. Dry climates limit incision and demand steeper channels. Glaciers and periglacial processes can impose a climate buzzsaw that caps mountain heights. Relief emerges from competition between uplift and climate-modulated erosion, often peaking at intermediate precipitation. Thanks for watching. In the next section, we will connect these ideas to specific mountain systems using data and models.